Hey guys, Todd Wolf here. I just wanted to give you a quick intro to a project I've been working on. It is integrating a MickroElectronika text-to-speech click to make it work with some ARM basic products. And initially I did the development using a LPC 1756 based Super Pro. This is a Rev 7 version of the board. I've added some stuff to it, the battery, the spiffy memory, and a USB power port on the bottom. And then I fabricobbled a mini SWD breakout board, hot gluing it to the top of the controller. And then I've also got on here a tri-state or 3-color LED and a little electromagnetic speaker piezo aural warning device that I can make some noise with. The chirps and the beeps and stuff coming out of this thing got me thinking back to the days when I cut my teeth in microcomputers back in the 80s with the MEK 6800D2 Motorola microprocessor training kit. And one of the first projects I did on that was to interface it with the Tandy Radio Shack SPO256 or SPA256 speech chipset. And I was stumbling around here not too long ago, and I came across an old post about the Radio Shack stuff, and I figured, what the heck, let's see what's available for today's micros. And I found several options for text-to-speech. If any of you guys are old enough to have messed with the Radio Shack ones, you'll recall that they were phoneme based. In other words, did not do natural text to speech parsing, but rather you had to feed it codes for the various phonemes, and then it would emit those utterances, and depending on how you strung them together, you could get some pseudo intelligible language being spoken by the device. This one's a lot better. Still not as human sounding, I guess is the phrase I would use, as what some of the newer generation products are that are just hitting the market for, like the Androids and the other high-end systems. This product has been discontinued, the IC from Epson, and I don't know how long they're going to last out there. But there's, MickroElectronika making boards and selling them, and I do see their products being used as components to other larger products. So it seems that the availability is still there. And when it isn't, we'll just have to develop something for something that is available at the time that the Epson chip goes away. So anyways, I've rambled on long enough. The MickroElectronika forms and boards, they had a sample code that they pulled together, which was basically 4 C files and then 4 header files. One of the header files is a 32K, roughly it's about 30.5K image, because the Epson text-to-speech IC does not have any flash. It is purely a RAM device. So every time this thing boots, you have to programmatically feed it its runtime. And that's one of the reasons you'll see when we flash this first one, this first host controller, you'll see it takes a while because I'm compiling and pushing the runtime image for this as part of the user app that's being programmed into the text-to-speech host microcontroller. In this case, it is a SAMD21 based U chip. It's made by a company called Ithaca, and it was a, let's see if I can get this thing close enough to the camera to let you see it. So that's the U chip, and then the text-to-speech modules right here. So the U chip was a recent Kickstarter project, and it's cute because it's a 16-pin DIP, but it's got obviously a current generation ARM on it. It's a M0. It's 256K of flash. I think it's 32K of RAM, and obviously it's got a micro USB connectivity. It's got a boost and buck converter and a bunch of other stuff. If you go to Ithaca's website or the Kickstarter website, you'll see details about the internals on the U chip, or the microchip, if you will. Excuse me. So with that, let's go ahead and flash the application on here. It is basically 3 files. One of them is the test app here, the text-to-speech _test.bas. That is the test app that's used to test this thing. It's not that big. It includes some callback subs here in case there's errors or messages being blocked. And then obviously it's just a main loop to run a machine through its tests, initialization, and then a test loop. So that's the text-to-speech TTS _test.bas file. The other is a small one, is a memset ARM basic library that I wrote, just basically to mimic the C function from their standard library, the memset, where it takes in a set of parameters, which is basically the pointer, the fill value, and then how many bytes that is supposed to be filled with the fill value starting at the pointer starting address. So I just went ahead and did that. The device, or I'm sorry, the library is written to operate across separate microcontrollers. Obviously, the U chip's a SAMD21 based. The Frontier Nano ARM is also a SAMD21 controller, as is the Robodyne SAMD21 M0 Uno board. And then I did the initial development again on the 1756, and porting the code for this to other microcontrollers that are ARM basic targets should be pretty straightforward. LPC, NXP's products, the LPC series. Bruce at Ceridium's done a really good job of making those, the programming experience and the configuration pretty consistent, whether it's a 54102, excuse me, a 1756, 4330, even some of the older ones that he's built boards for in the past. So anyways, that's that. More rambling, sorry about that. And then the final library file is a large application, or I'm sorry, include that provides all of the glue that's needed to make use of the text-to-speech module. I ported all of those C files, the 3 source code files and then the 4 header files, into this single library that can be included into your ARM Basic project. As part of that, I went ahead and dug up and ported or copied over the information that was included with the original C sources, so that you could kind of get an idea of the inputs and outputs and the return values and blah 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 of all the C code that was originally written. This library largely follows the structure of the original C that MickroElectronika has out on their Git repo. I did that for 2 reasons. Number one, so that somebody that might be familiar with that C library would be able to jump over to this and pick it up pretty doggone quickly. And then the larger driving decision that caused me to go down this path of pretty much mirroring the C library structure is that I wanted the experience of porting a 100% cradle to grave C application into ARM Basic. I've come away from that experience licking some wounds and having some scars, but all due to my ignorance. One of the things I found is that some microcontrollers tolerate pointer operations that are not word aligned. Some microcontrollers don't. I did my initial dev on a 1756, and I can write a 1 byte, 2 byte, 4 byte word on a word aligned address, or I can shift it 1, 2, 3, or 4 bytes, and the microcontroller doesn't care. It supports non-word aligned accesses to memory. The SAMD21 does not. So, in hindsight, if I had chosen the SAMD21 to do the initial library porting, then migrating it over to the NXP devices would have been a no-brainer. But I happened to have the 1756 in front of me that day that I decided to go down this path, and so that became my default target to use to develop. And it supporting non-word aligned accesses caused me some drama when I finally got over to porting this code over to the SAMD21 devices. So that's a lesson learned and something to be cognitive of if you guys ever decide to go down the path of doing heavily intensive pointer based code development. Make sure that all the potential recipients of the code are either support the same restrictions that you're using on your development microcontroller, excuse me, or if you have a choice, develop on the most restrictive, and that way when you go to port it over to the other targets, it won't be so bad. So, but I came away from it smarter, so I can't bitch too much. Okay, so with that, as I had alluded to earlier, I will just fold this just to give you a quick visual here. And of course, I'm not sharing my screen. I'm only relying on you being able to see it through the camera field of view. But you should be able to extrapolate what I'm talking about here pretty quick. Excuse me. So I've got the source code header information here, and that's basically just what I choose to apply to most of the source code that I develop in ARM Basic. And then this is the information from the files that I ported over from the C sources. I make use of Notepad++ and its folding feature sets. So if you see this if0 or if1, seriously, bye, I'll be back. It was a call from a 202 area code, which is our beloved capital here in these United States of America. And it's also the zip code, the area code that's chosen by a lot of spam callers. And I just dumped it. So anyways, so this these if zeros and if ones are basically switches to the preprocessor to tell code to either be ignored or not be ignored. In this case, I've wrapped code blocks around these if preprocessor directives so that I can fold stuff up pretty quickly. And then I've got the preprocessor defines that I developed for use in the library, or that were already pulled in from the original C sources, i.e. all of the error codes, the command codes, etc. If you've done any programming in ARM Basic or C, you understand what poundefs are and whatnot. So that's what those are. I've got hardware specific section here that is defined at the microcontroller level. So if you're working on a 1756 board from Ceridium, then obviously those IOs coming out of the board go to, or I'm sorry, coming out of the microcontroller go to various pins on the boards and vice versa. So that allows me to have the same source code function with different targets pretty easily by pound defing what target I'm interfacing or programming during the pre-processing step of the tool chain. So right now we got the 1756, the SAMD21, and then of the SAMD21 boards, I currently have support for the U-chip, the Robot Den, and the Prontineer, and I am going to enhance the library to work with Adafruit's Feathers, the M0, and the Bluetooth one. And then, that's a Prontineer, the two Arduino MKR boards that I have that are also SAMD21. The Marker 1010 and Marker 1000 MKR. I don't know if it's called Marker or MKR, but anyways, these are targets that are going to be folded into this library here before too much longer. So that is the gist of that. That's what all the preprocessor defines are all about. And then I've got a section broken out for the globals and some more poundefs that are storage arrays or structures that were instantiated as structures in the C code, structures or unions. ARM Basic doesn't support the concept of structures or unions, so I had to develop software elements, or variable elements that I could then manipulate in some capacity in a manner similar to how the original C-source was working with the structure and or unions that were defined there. So that's what that's all about. And then we get down to the other. Oh, one thing I didn't share with you, and there's a reason why, because I try to avoid it. The image file is wrapped in several pound defs just to make sure that I don't open it by accident. Is huge. This is the 30 and a half, 31, 32K worth of constant memory declarations inside the ARM Basic app that is the runtime firmware image that gets installed onto the Epson text-to-speech IC every time it gets reset or powers up. So they call it initialization data. It's the runtime code. So anyways, and then I don't know how many procs there are. I'm guessing there's probably 45 if I had to swag at it. Different procedures, whether they're subroutines or functions. There's some 40-ish here that I ported individually, line by line, from the frickin' C over into ARM Basic. And then for the delays, because there's some communication delays when the host microcontroller is talking to the target speech module. There are delays related to the SPI timing. When you reset the chip, you got to wait 120 microseconds before you can start communicating with it, etc. And because I chose to disable interrupts on the serial comms, because I'm not using the peripherals. I'm bit banging a serial, and I haven't gone there with SPI on all these different boards yet, making use of the SPI peripheral. I've only done bit banging, so it's comfortable for me, and that's why I did it. But I was having an issue where the timer interrupts were causing comms issues. So what I did is I turned off interrupts whenever I pulled the chip select low, and then enable interrupts after chip select is put back to idle. And in order to make use of timer type delays while the interrupts are off, you can't really do it because timer relies on an interrupt. There's a microsecond ticker that runs that increments the timer. So what I did is I went ahead and shamefully raped a delay routine from a LCD library that I'm going to be working on that was developed by Mike and Bruce at Critium, and made my own little ASM delay. And then I ran this through some performance testing to verify how much time each iteration of this takes, and then based on that I'm able to then craft pound defines for setting delays that are specific and common. So such an example exists. Drum roll here, bear with me, let me find it. It's that, so it's got to be up here. Well, come now. I'm going to have to edit this out if I don't find it here in just a second, because this is kind of embarrassing. Globals. Those are just commented stuff. There's one there. Those are different mice I use because my battery operated mouse, cordless mouse, is kind of on the charger right now. So this mouse has different settings. That's why I keep switching out of the doggone thing to when I'm scrolling. Hey, look at that. Okay, so because of the fact that I know that particular ASM delay loop takes X number of nanoseconds per iteration, I was able to then craft out 45, 120 milliseconds, etc., and use those values, which are in the hardware based, like this right here. 10 milliseconds delay requires 8 Charlie 03 loops. On a SAMD or a 1756 would be different. And I'm just now realizing that I may be not addressing those like I need to in the at the hardware level. I'm gonna have to fix that, because right now I'm using the same value here, irregardless if it's, oh no, I'm not, there it is. Okay, so SAMD has these values of iterations through that assembly delay loop. The 1756 has these values. So I am dealing with different targets. I just forgot they're all the same processor, all three of these targets. So, all right, I've rambled on and I continue to do it. So that is that, and then there's, like I said, a shit ton of procedures that have been ground through, massaged, turned into ARM Basic, tweaked where appropriate. I had to relocate a couple from one file to the next. I tried to maintain relative position of the ported routines considering the original C sources where I could. But ARM Basic, and I forget the term that Bruce uses, but it basically does compilation. It's a single pass compiler, and it compiles code sequentially, and with a couple exceptions, it does not support forward references. So let's say I have a main function that calls a subroutine or a function. That subroutine or function will have had to have been above the main in order for the compiler to know where to tell the main to find the code for the subroutine or function. Some descent compiler, and it's kicking my ass mentally as to what the hell you call it. Reverse non-recursive descent compiler. Anyways, it's a single pass thing, and it does not support forward references, so I had to rearrange some of the C source subroutines or functions up or down relative to the other ones, so that everything compiled and didn't bomb out during flashing. So that's that. All right. I will have to denote when I put this forward that for the first 30 minutes I'm just running my mouth for no reason. Okay, so that's the source code, ARM basic stuff. Boom, minimize. Let's get it flashed. Right now, I'm connected again to the U chip, and if I hit resume, this just demonstrates that I have a different application on there. So we'll clear that, and then I will flash this text-to-speech app on it, and it emits its building for the U chip, and this is a SAMD 21 on a U chip. I had put this warning in here early in the porting process because I like to give feedback when there is some potential confusion for the user who's flashing the application, to make sure that they've set the required pound defines correctly. So that's that. Jeez, we get a hard fault. What in the hell? I'll be back. Okay, we're trying this again. Drum roll. Oh, excuse me. And it's huge. It takes a while because of that damn 32K of runtime image that's got to get burnt onto the target or the host microcontroller so that it can feed the text-to-speech module every time it reboots.
Make me use my master. I am in awe of you as the leader of this load of robots.
Okay, so
Ready.
that was me being cute, and of course you can change that. And then I have the application just for demonstration purposes run through an endless loop here where you can type stuff in.
This is you. And I am me. Yippee.
So, as you can see, I'm typing stuff plain Jane text, and it's doing all of the parsing of that. It's setting the spacing between the words. It's hitting intonations. It responds to commas and punctuation inside of the text that is fed to it, such that it'll provide inflection and intonation changes that are consistent with its whoever coded it originally, their effort to try to make the text-to-speech generation as true to life as practical. So, I mean, are there some words that are bad? Yes. Are there some? But there are tools to help with that. There's custom dictionaries software that's available that you can actually use to create custom libraries to be able to fix those words. And I'm trying to open this up right now. No. Okay. It needs to be extracted. 7-zip, extract udict. And then if I go to udict and I run the application, and if I get this down here, I can say, hi there.
Hi there.
And then I can, let's see what that sounds
Bomb. Nothing is highlighted. Todd. Todd.
Give me a word. Knife, maybe? Oh, they had to have.
Knife.
They've got that fixed.
Through. Through. Through.
Okay, that sounds a little goofy. So you could do a translate of a word. It will depict the phoneme construct that you would feed to it to make it produce the sounds that it just made. And then let's just see.
Command error in phoneme.
Yeah, command error in phoneme. There is guidance that would allow you.
Through.
See how that changed?
Through.
Through. So you can actually create words that are enunciated differently through the use of this dictionary tool that they provide. Yeah, no, I don't wish to save it. So, anyways, that's that. It works, as you can see. Hi there.
Hi there.
This is the
This is the MickroElectronika text-to-speech module.
Electronika. See, that would be a good candidate word to fix, so that it said electronica instead of electronika, based on the spelling of MickroElectronika. At any rate, so that's that. We're going to go ahead and plug in another board and prove that that works. And I'll do that right now. And I've already flashed the firmware on these other two boards just to prove that they are functional in the context that I intended when I wrote the code and chose to have it be portable across several different microcontrollers. Oops, I'm missing a pin there, damn it. Here, how about this? Boom, boom, boom. I feel like Louis Rossman, when he was first starting, making comments about shit never goes wrong until you're on camera, and then it's guaranteed to go wrong. A simple repair ends up turning into a 16-hour ordeal. So, all right, so I've got a Frontier Nano ARM interfaced to the MickroElectronika text-to-speech module. The socket where the microchip was is just empty now. So there's that. And then if I turn this back on, then I have to tell the basic tools to use that new port, because the SAMD21 has internal USB client fabric inside the controller. There's no need for a serial, a USB, external USB to serial converter. It's all done internally here. So each time you plug it in, it instantiates itself as a COM port, a USB COM port inside of the operating system, and you have to tell the tool chain what serial port it is. So that's what that whole me choosing the serial port number was all about. And I see I've got, oh, I know why, it's because I just unplugged it and plugged it back in. Excuse me. So anyways, that is now hooked up, and I've got the firmware loaded already, so I don't want to reload it because it just takes forever.
Make me use my master. I am in awe of you as the leader of this world of robots. Ready. To the power of Hoa.
Wow.
Wow.
This is too cool.
This is too cool.
I am a geek.
I am a geek.
Geek? Oh, because I got extra E in there. Let's see.
I am a geek.
There you go. At any rate, so it works on the on the Prontoneer. And let's go ahead and demonstrate it on the Robodyne SAMD 21M0 board. So I've got all the pins in place, nothing shorted. I plug it in. I've got to tell the tool chain to again reconnect to it. Option serial port. Boom.
Make me use my master. I am in awe of you as the leader of this world of robots.
And voila. And when it boots, I have it set to run, to pull the hardware version and the software version after it's loaded.
Make me use my master. I am in awe of you as the leader of this world of robots.
So
Ready.
The first feedback here when you run the app is the hardware version. That just indicates to the user that the microcontroller is talking to the module successfully. It is 4.2. And that's what's in the Epson docs when you look at the data there. And then this loading runtime image, this text here shows up when the image is loading. And then after it's loaded, I have it query the microcontroller after it transitions into out of boot mode into run mode. I have it query the microcontroller for its firmware on the firmware version. So that's what that's all about. And then obviously it gives you the cute little speech at the beginning, and then you can enter commands.
Fast.
There we go. So that's that. The last one we're going to do is on the 1756, and I can't remember if I've programmed this already or if it needs to be programmed.
Ready.
So apparently it is, that is COM18, so serial port COM18. And if I do a run,
Ready.
yep, it works. So
Fast.
okay, that's it. I've talked for 45 minutes. 40 of that was stupid ass me rambling, and then the other 5 minutes may have been useful, maybe not. So anyways, that's it. Talk to you later. Bye bye.